I'm so excited, folks. This is another one of those tests that I really enjoy using whenever I do have the opportunity to use it. Unfortunately, opportunities to use this test are relatively few and far between, but when you can use it, it's so fast and so clean. It just feels so good. So today's material is probably going to be relatively short. We're only going to cover alternating series test, because what I want to do today is have a slightly longer exercise set so that you can get practice deciding which of our many tests to use given any particular series. So by the end of today, we should be able to define this term, alternating series. We should be able to use the alternating series test to determine convergence/divergence. Of course, as always, determine when that test can be used appropriately. And then in the exercises for today, practice deciding what test of our many tests you should use for a particular problem. Folks, I don't know what I was thinking. I recorded like the entire video for the alternating series test. I edited it, I uploaded it, and then, only then, did I realize that we had this entire second half of material that I had not addressed in the video. So the previous set of learning objectives actually is incomplete. We have a few more things that need to be done today in order to stay on schedule. Namely, we need to, first of all, talk about some ways to do estimates for the value of a series when our series is alternating. We need to talk about absolute convergence and conditional convergence. So two sort of sub-varieties of convergence. And then finally, we're going to get some practice, both in today's video and in the exercises, addressing this conditional convergence and absolute convergence issue. So here is the setting. Here is our motivation for this test. Consider series like -1 to the power k divided by k, or cosine pi k divided by k squared. The series, not telescoping, they're not geometric, and they're not p-series. So all of the tests that we have and the theorems that apply specifically to those kinds of series are not applicable here. The divergence test is locked because these terms do converge to 0 as k goes to infinity. We can't use the original definition because we can't really find a formula for the nth partial sum. Not only that, we can't use the comparison tests from yesterday either. The reason being that the comparison test required us to have entirely positive terms for our sequence. But the sequences here are both positive and negative, depending on the parity of the number k. Depending on whether k is an even number or an odd number, the terms in the sequence will be either positive or negative. So in situations like this, let's introduce I suppose this is the 8th test for us, called the alternating series test. And the first thing that I want to tell you is exactly what is an alternating series. An alternating series is any series whose terms alternate between positive and negative. So if one term is positive, then the next one must be negative. And if one term is negative, then the next one must be positive. Symbolically, I would say if ak is greater than 0, positive, then the next term, a sub k plus 1, must be negative. And if your a sub k is negative, then the next one must be positive. Forcing it to exactly alternate plus minus, plus minus, plus minus. For examples, we could take either of the two on the previous page. If we sum that from k goes from 1 to infinity, when k is equal to 1, minus 1 to the first power produces minus 1. But when k is 2, minus 1 squared produces positive 1. Then negative 1 when k is 3, positive 1 when k is 4, and so on. And we can see this exact alternation, minus, plus, minus, plus, minus, plus, and so on to infinity. Now the other one may not initially look like it's alternating, because where is the minus 1 in this expression? However, if we plug k equals 1 into cosine, then we get cosine of pi, which is on the left side of the unit circle, so that has an x-coordinate of minus 1. If we plug in k equals 2, then we have cosine of 2 pi, which is on the right side of the unit circle, so that x-component is positive 1. Then when k is 3, we're back on the left side of the unit circle, so we're back to having a minus 1. And so on and so forth. So in general, if you're checking to see whether your series is alternating, you're generally looking for an expression of the form minus 1 to the k times a positive series, a positive sequence, or sometimes minus 1 to the k plus 1 times a positive sequence. Or sometimes minus 1 to the k minus 1. In general, minus 1 to some power times positive sequence This is the format for an alternating series. The alternation in sign comes from minus 1 to some power. As k flip-flops between even and odd, minus 1 to some power will flip-flop between positive and negative. The only thing to really be careful of is that sometimes minus 1 to the power k is in disguise. For example, cosine of pi k actually works out to be exactly equal to negative 1 to the k. These two quantities are identical for every integer k. They don't match up when you allow k to be any real number, but if you allow k to be only the whole numbers with no decimal part, these two expressions will always match up in value. For example, when k is 1, both of these quantities produce minus 1. When k is 2, both quantities produce positive 1, and so on and so forth. So that's why we have this second expression here. It doesn't contain negative 1 to some power, but it contains that in disguise, in the form of cosine. Once you have an alternating series, it becomes very, very easy to determine whether or not that series is converging or diverging. There's really only a little bit that you need to investigate. You have some series, sum of ak, that you need to determine whether it is converging or diverging, and you know in advance that this series is alternating. Now, if you look at only the positive part of the sequence of terms, if you look at the absolute value, if that sequence of positive terms is decreasing, then all you have to do is look at the limit of the magnitude. If the limit, as k goes to infinity, of the positive part of this alternating series is equal to 0, then the series converges. If the limit does not equal 0, then the series diverges. So this is almost like the blessed version of divergence test. Divergence test told you that if the limit of your sequence was non-zero, then the series had to diverge. However, divergence test does not give you any information at all if the limit of your sequence happens to be zero exactly. However, if you're very, very lucky, and you happen to be in this situation where you have an alternating series, then the alternating series test steps in as a new and improved edition of divergence test, which says, yes, if the limit of the sequence is non-zero, then the series does diverge. But not only that, if the limit of the sequence is zero, then the series must converge. Let's practice applying that to each of the following two series. The ones from the previous example, -1 to the k over k, and cosine of pi k over k squared. Now looking at this first sequence, if I take the absolute value of -1 to the k is always equal to 1. Because -1 to the k is either equal to +1 or -1. In either case, the absolute value is +1. So, note that this sequence of absolute values is decreasing. And not only that, if I look at the sequence of absolute values, that is approaching 0 as k goes to infinity. So by the alternating series test, this series must converge. I suppose there are a few things worth pointing out about this example. The first thing is that the alternating series test was unlocked even though div test remained locked. So even though div test was not useful at all here and was completely inconclusive in this case, because we specifically had an alternating series, we could use the alternating series test to conclude that this series must converge. The next thing that's kind of neat about this example that's worth paying attention to is that the sum of -1 to the k over k, the alternating harmonic series, converges even though if we had only positive terms and we had 1 over k, we would get a divergent series. So if you sum up all the terms of 1 over k, all those terms are positive and they're large enough that the end result goes to positive infinity. But if you take that series and you just sprinkle a couple of negative terms in there, if you make every other term negative, the negatives and the positives will cancel out enough that the sum of -1 to the k over k is a finite number, even though the sum of 1 over k is an infinite number. Let's try the same thing here with our friend cosine of pi k over k squared. Once again, if we look at the absolute value, if we look only at the positive part, ignoring the cosine pi k, which is equal to -1 to the k, then I get the sequence 1 over k squared, which is decreasing, and which approaches 0 as k goes to infinity. Because the original series is alternating, the alternating series test kicks in, and it implies that the series converges. Let's have a look at the final series where we have the sum of -1 to the k times 2k over natural log of k plus 1. Now, my instinct here is to say, this series is alternating, so let's see if we can use the alternating series test. So stripping off the -1 to the k part and looking only at the positive part, we have the sequence 2k divided by natural log of k plus 1. Now, although it may be tempting to use the alternating series test here, we're going to run into a problem because this sequence of terms is not decreasing. K is growing larger than natural log of k as k goes toward infinity. So I think that this particular sequence of terms is actually increasing rather than decreasing. So perhaps there is another test that might be more conducive to this situation. If I looked at the limit as k goes to infinity of the original sequence, because this positive part is growing in size, then the sequence in this problem is just flip-flopping between increasingly large positive numbers and increasingly large negative numbers. So based on that, the limit of the original sequence does not exist. And because of that, the divergence test kicks in and says this series does not converge. So just be careful about that. If you are going to use the alternating series test in your argument, there are a few things that absolutely need to be checked. First, you want to make sure that your series is in fact alternating, but there was a second part of the hypothesis which says that the absolute value of the terms in the sequence has to be decreasing. So if that condition is not satisfied, alternating series test is not the one that you need to use to justify your conclusion. You'll need to use something else, such as divergence test, to justify your conclusion about the series. On those same lines, let's consider the following exercise. Is the following use of the alternating series test logically valid or logically invalid? They say the series cosine n over n is alternating because you have that cosine there, which is going between positive and negative. And because the limit as n goes to infinity of cosine n over n is equal to 0, they conclude that the series must converge by the alternating series test. What do you think? Is this correct or not? I think that this one is incorrect. Not only is there something missing from their argument, there's something that they have stated that's actually completely wrong here. That's actually false. First, they never checked if the absolute value of cosine n over n is decreasing. So that's one glaring omission there. But something that they have stated that's actually completely wrong is that the series cosine n over n is alternating. Notice that unlike in the previous examples, the cosine in this problem does not have a pi in the argument. This is not cosine of pi times variable, this is simply cosine of variable, which means that the first term in this sequence cosine of 1 is different from cosine of 1 times pi. Cosine of 1, treating 1 as 1 radian, is not going to simplify to a nice whole number. According to my calculations off to the side, this works out to be about 0.54, positive number. Now if I look at the next term here, cosine 2 over 2, cosine of 2 radians works out to be negative 0.42, approximately speaking, and that's negative. So far, yes, so far we do have an alternation, but let's have a look at cosine of 3 and cosine 4. Cos 3 over 3, cosine of 3 radians is negative 0.99. So cosine 3 has exactly the same sign as cosine of 2. So the alternation fails in this step. Because I had two subsequent terms with exactly the same sign, this series is not alternating. So a huge flaw in the student's argument is that they tried to use alternating series tests on a series that wasn't even alternating in the first place. So this is a logically invalid use of the test. So recall from, I guess, the integral test video number 6, that if we had a series whose formula for the sequence was continuous, positive, and decreasing, and sufficiently nice that we could integrate the formula, then we had this error estimate. We had this calculation that we could do to estimate the worst case scenario error that we incurred if we were estimating the series using the nth partial sum. Now notice that that particular error estimate could not possibly be used on any alternating series, because alternating series, by definition, have some negative terms in the series, and therefore the series is not entirely positive, and that other error estimate could not be used. For an alternating series, we have a different estimate, though, that can be used to get an idea of how far our nth partial sum is from the true value of the series. So let's suppose that we have an alternating series sum of AK, which we already know does converge to some value, and now we're trying to figure out to what value might it converge. Let's also assume that the absolute values of these terms, the magnitudes, are decreasing. I'm going to use the letter L to represent the series' actual value, the value of that limit. I'm going to use S sub n to represent the nth partial sum. If we estimate the value of L using the nth partial sum, then what can we say about the error? What can we say about the difference between the actual value and the estimated value? The error cannot be any bigger than the value of the very next term in the sequence. If you estimate using the partial sum S sub n, then the difference between S sub n and the limit L is bounded above by the absolute value of the very next term in the sequence. This is a hugely convenient formula. You don't even have to calculate any antiderivatives or integrals. But once again, this convenience comes at the cost of we have to have an alternating series in order to actually use this estimate. So let's practice using that formula in the following example. We have the alternating harmonic series negative 1 to the k divided by k, which is being summed from 1 to infinity. And we already knew from the alternating series test that this series is convergent. But the question is, what number does this series converge to? And so that is what we will be trying to understand in this problem. There are two parts. The first thing that we want to do is we want to figure out a value of n so that the nth partial sum is no more than 0.0001 units away from the series' actual value. So for part 1, the goal is to have the error less than or equal to 0.001. And in particular, the worst case error. If we're really unlucky, if we're in the worst possible scenario, we still need that error to be less than this 0.0001. Now, once we have determined the value of n that actually guarantees that, the next thing that we need to do is we actually need to calculate S sub n. Let's use the fact that the worst case error, the worst it could possibly be, is equal to the absolute value of the series at the very next step, a sub n plus 1. So let's plug capital N plus 1 in for the variable k in the formula for our sequence that we're summing up. We have the absolute value of -1 n plus 1 divided by n plus 1, which simplifies to positive 1 over capital N plus 1. And our goal is to make that less than or equal to 0.0001. So in other words, we want to make sure that 1 over 0.0001 is less than or equal to n plus 1. And if I remember correctly, 1, 2, 3, 4, 1, 0, 0, 0, 0. This means that n plus 1 will have to be greater than or equal to 10,000, which means that n itself is going to have to be greater than or equal to 9999. As long as I calculate an nth partial sum with an n that is larger than this number, as long as I have at least 9,999 terms in the partial sum, my estimate will guaranteed be within 0.0001 units of the true value of the series. Let's go ahead and let's calculate the S sub 9999, which is the sum as k goes from 1 to 9999, -1 to the k over k. Now, by no means would I ever expect you to do this by hand. I, in particular, am going to pause the recording, go to Wolfram Alpha, and do it over there. Just in case you've never used Wolfram Alpha before, this is how you could quickly calculate the value of such a sum. All I've done is I've gone to Wolfram Alpha, and I have typed into their search bar sum as k goes from 1 to 9999 of -1 to the power k divided by k. So it interprets that as, here it is in sigma notation, and it says, okay, we did that work via computer, and here is the result that we calculated. It is roughly -0.693197, etc. Which I'm going to round to, let's say, 4 decimal places. So here is our estimate, and note that that implies that the real value L must be between, well, it must lie within 0.0001 units of this sum that we calculated. So if I go up from that number, then I'll get -0.6931, and if I go down from that number, I get -0.6933. So the true value of the series must live somewhere between these two values. And if I wanted to narrow in on the series even more, I would have to take a partial sum with even more terms in it. Now, just as an interesting note, it turns out the real value of this series is equal to the natural log of 2. And I don't know about you all, but looking at this decimal approximation, it would never have been clear to me that natural log of 2 is equal to the real value of this series. But actually, as we start to go forward into the next couple of sections, where we're talking about power series and Taylor series for functions, we'll actually develop some techniques to figure out why a series like -1 to the k over k is actually exactly equal to the natural log of 2. Okay, the final thing that we need to talk about today is absolute convergence and conditional convergence. And what we're trying to get at in this section of the material is a situation like we saw a few pages back, where the sum of the alternating harmonic series converged, even though if we stripped away that alternation, if we looked only at the positive part of the series and considered the harmonic series instead of the alternating harmonic series, this guy diverge. Just by adding in a couple of negative numbers, by making every other term in the series negative, that was enough to bring the value of the series all the way down from positive infinity down to a finite number. In general, it is much harder to make a series converge when all the terms are positive. If all the terms are positive, no cancellation is happening, and so you're much more likely for the series to have an infinite value. And let's capture that in the following theorem. If you can get the sum of the absolute values to converge, then the original series without the absolute value must converge as well. If you can get the difficult series to converge, then the easy series must converge as well. In other words, it's harder to make the sum of the absolute values converge than it is to get convergence if you're allowing to have some negative numbers involved in your sequence. Which brings us to the following definitions. Two varieties of convergence. The first variety of convergence is called conditional convergence. We say that a series converges conditionally if the original series converges, but as soon as you put absolute values on the sequence, the series with the absolute values on it diverges. Called conditional convergence because the series converges with the condition that there are some negative terms in there somewhere. For example, the series that we had -1 to the k over k converges conditionally. This series with the -1 to the k does converge, but as soon as we change that -1 to the k into a positive 1, then we get a divergent series, so we lost our convergence as soon as we put an absolute value into the mix. However, if your series is absolutely convergent, then this is a series whose convergence is fairly strong and resilient. Not only does your original series converge, but if you stick the absolute values on there, that series converges as well. So-called absolute convergence because it converges even with the absolute values on there. Now notice that for any particular series sum of AK, there are three mutually exclusive possibilities. Exactly one of these is true at any given time. Option number one is that the original series diverges. Option number two is that the original series converges conditionally. What this means is that your original series converges, but if you stick absolute values on there, all of a sudden you have a divergent series. And the third mutually exclusive possibility is that the series converges absolutely. Which amounts to saying that the sum of the absolute values of A sub k is a convergent series. So let's practice checking which of these three cases holds for a few example series. So in this problem we have the series -1 to the k divided by square root of k. Now when I'm asked a question like this one, conditional convergence, absolute convergence, or divergence, the first thing that I tend to check is, does the original series converge? If we take the absolute value of the terms in the sequence, getting rid of that -1 to the k, then we get a decreasing sequence. As k goes to infinity, this quantity goes to 0. The original series converges. Why? Because of the alternating series test. So that means that it's no longer possible for this series to be divergent. We have eliminated that option. And the next thing that we need to determine is this series conditionally convergent or absolutely convergent. Which one of those two remaining cases is true? So the next thing that we need to do is we need to ask ourselves, does the series of absolute values converge? In other words, does the series of 1 over square root k converge? But notice that this series, where we've taken the absolute value and we've stripped away the -1 to the k, is a p-series, because the square root is the same thing as a power of 1/2. So by the p-series test, because that power is something that's smaller than 1, this series diverges. So the original series converged, but as soon as we put absolute values onto the terms in the series, we lost our convergence and we ended up with a divergent series. Which means that this particular series, -1 to the k over square root k, converges conditionally. It converges subject to the condition, subject to the requirement that we maintain some of those negative terms in the mix. Let's try it with this one. We have the sum of -1 over 2 to the k. That this series is geometric, with a common ratio of -1/2, which is less than 1 in magnitude. So because of that, the original series must converge by the theorem on convergence for geometric series. So once again, we're left with two possibilities. the series converges conditionally, or the series converges absolutely. So next thing we're going to do is we're going to investigate the series where we put absolute values. Now notice that if we take the absolute value of -1/2 to the k, that negative sign will be eliminated by the absolute value and we'll be left with something equivalent to the sum of +1/2 to the k. But this is still a geometric series, and the common ratio is still less than 1 in magnitude. So the series with the absolute values converges as well. So because the series with the absolute value must converge, then we can conclude that our original series converges absolutely. For a final example, let's consider the sum of sine k. Now, looking at the series sine of k, if I take the limit as k goes to infinity of the terms in that sequence, then that limit does not exist because this quantity keeps oscillating. Because of that, the divergence test is unlocked. What? Folks, I don't know why it's doing this. This computer keeps eating what I am trying to write. I've been writing the same thing over and over again for the past several minutes, and it keeps disappearing. Let's try one more time. Limit sine dne series diverges by div test. So far so good. And once you know that the series diverges, your work is done. It's the it's the third of the mutually exclusive possibilities.